What we want to do in exercise 3.4 is compare the strength of different acids. In other words, is this hydrogen more likely to come off of this molecule, or is this hydrogen more likely to come off of that molecule? Which molecule is more acidic? Which is better able to donate a hydrogen, an H+? And you can do that quantitatively. You can compare how strong different acids are quantitatively with things called Ka and pKa. Just so we're all on the same page about what those mean, let's review just for a second what they are from general chemistry. So in general chemistry 1, you had a reaction, and the arrow was very simple. Either all the reactants turned into products, and so the reaction happened, or you didn't have any reaction at all. So reactions were like light switches that were either completely on or completely off. And then, in general chemistry 2, you refined that idea a little bit. You were dealing with things in water a lot. And so the reaction would happen, but the pieces that you get would still be bouncing around, moving around in the water. And every once in a while, they'd bounce around in just the right way to turn back into the things they were originally. So that the forward reaction and the reverse reaction were happening at the same time. They happened, the reaction went forward until the rate of the forward reaction and the rate of the reverse reaction were the same. And that was called equilibrium. A nice analogy for equilibrium, you can think of a nice analogy by using a sort of water tank. So imagine a water tank where the water on the left here is going to the right. After all, if you put a drop of, say, dye into this left part, it would eventually spread out. And so you know that the water is moving that way. But at the same time, the water on the right side is moving to the left. If you put dye there, it would eventually spread out too. So the water is moving to the right and to the left at the same rate, and so it looks like nothing's happening. That equal rate of forward and reverse reaction is what equilibrium is. Equilibrium does not mean that you have equal amounts of reactant and product. Just like in this water tank, you have a larger amount of the water on the right than on the left. It's the rates that are the same of them turning into each other. So that begs the question then. So in general chemistry 2, if in general chemistry 1, reactions were like light switches that were either on or off, in general chemistry 2, reactions became like dimmer switches that would go forward. They would become sort of brighter or dimmer, depending on the specific reaction, because they also went backwards. And so the question is, how bright is the light? How far on does it go? How many products do you make before they start leaking back and turning into reactants at the same rate? And that was unique for each reaction. You described it quantitatively in general chemistry with a constant called K, and this is a capital K. It's called the equilibrium constant, because it's a constant that describes how much stuff you have when the rates are the same, when you have that equilibrium for the forward and reverse reaction. So the equilibrium constant K. Conceptually, that was products over reactants. So let's think about what that means. If K is equal to 1, then that means you have equal amounts of products and reactants. If K was a big number, like 1,000, then you have more products than you have reactants. And if K was a small number, like 1,000th, then you have more reactants than products. So K is a number that tells you how far forward this reaction goes, how bright that dimmer switch is in an equilibrium. In general chemistry, you would have seen lots of different types of K, Ka, Kb, Kw, Ksp. They were all products over reactants. And those little letters were just telling you what type of a reaction this was. If that reaction is an acid, So a molecule that has an H to give away. Then the equilibrium constant for it would be something called Ka. A for acid. And that's all there is to that. So Ka tells you how far forward an acid dissociation goes. This acid breaking apart, how far forward does that go? If an acid is really strong, then it will break apart a lot. You'll have a large amount of products and very few reactants. In other words, you'll have a large amount of products and very few reactants. K will be a big number. So let's summarize that in a table. Here if you have a strong acid, then the acid will give away all its H's. You'll have mostly products, which means the top will be big, bottom will be small, and Ka will be big. The bigger the Ka, the stronger the acid. If an acid is weak, then you'll have mostly reactants. You'll have very few products. Most of the molecules won't give their H's away. The H will stay on the molecule. So if an acid is weak, then you'll have mostly reactants. In other words, you'll have a big number on the bottom, a small number on the top. That is a small number, 1,000th. In this example, I'm just coming up with a number there. 1,000th. So if you have a weak acid, then Ka is a small number. Okay. Now the Kas were usually awkward numbers, or really big numbers, or really small numbers. Things like a Ka that you might have seen might have been something like 10 to the negative 12th. Or another one you might have seen, it might have been like 10 to the negative 6th. The numbers were really non-intuitive. It's hard for me to imagine what 10 to the negative 12th looks like. Now you can compare these, though, using our little concept here, our little table. 10 to the negative 12th is a smaller number than 10 to the negative 6th. That's a relatively bigger number. Right, this would have just 5 zeros there. This would have 11 zeros. So this is a bigger number than that is. So, because this Ka is bigger, that would be a stronger acid. Now, one of the ways to make it less awkward dealing with such crazy numbers is to take the logarithm. This was a technique you learned in general chemistry also. Instead of just having this weird 10 to a power, you can solve for an exponent by taking a logarithm. So if you take the log of a number, you end up just with whatever the exponent was. So the log of the Ka here would just be negative 12. And the other one, if you took the log of this Ka, it would just be negative 6, the exponent. Logarithms solve for exponents. So that definitely makes the number more intuitive. Easier for me to imagine negative 12 than 10 to the negative 12. But it would be even more intuitive still if I took the negative, because that would get rid of the negative there. If I took the negative of that, if I multiplied both sides by negative 1, it gets a negative there, and now it's really intuitive. I can picture 12. So I took a non-intuitive number, and I made it intuitive just by taking the negative log. Okay. Now, That technique of adding the negative log to turn non-intuitive numbers into intuitive ones was done a lot in general chemistry. We are galactically large. Every time you exhale, you breathe out more atoms than there are stars in our galaxy. If the ocean were made of blueberries, from the depth of the ocean to the surface, all over the Earth, that number of blueberries is smaller than the number of water molecules in one drop of water. When we deal with just what seems to us like tiny amounts of stuff, we're dealing with huge numbers of atoms, and so when we try to talk about them, we end up with these crazy non-intuitive numbers all the time. Which means this technique of taking the negative log to make numbers more intuitive was something that we did all the time. And because you do something all the time, just like somebody you might know really, really well, you see them all the time, you come up with a nickname for them. And the nickname for that negative log is a lowercase p. So the negative log of the Ka, you could say that same thing by calling it the pKa. That's 12 for that left one. Or again, the negative log, that lowercase p, pKa here, would be 6. That p is the same p that you saw in pH. The pH is the negative log of the concentration of H+ in a solution. Just making it more intuitive to count up those atoms. And you saw it in other places too, the pOH, etc. Notice what happened when we took the pKa though. The smaller Ka gave us the bigger pKa. Notice, this pKa of 12 is big, whereas 6 is small, if you're comparing these two. The smaller Ka gave us a bigger pKa. Now we saw before that if you have a small Ka, you have a weak acid. We just saw now that if you have a small Ka, you're going to have a big pKa. And so we get these two features of a weak acid. A weak acid would have a small Ka and a big pKa. Whereas a big Ka, so now we're talking about strong acids, a big Ka would have a small pKa. So this table lets you compare acids, the strength of acids, quantitatively. You would be given a Ka or a pKa, and you'd be asked, which is the stronger acid? The bigger the Ka, or the smaller the pKa, the stronger the acid. So, now we're finally ready to look at this problem. Once you understand all of those concepts, solving these problems is relatively straightforward. It says for each pair of compounds below, identify the more acidic compound. So what are we looking for? More acidic, that's either bigger Ka or smaller pKa. So let's write the pKa's down, or the Ka's. Now, this is a table from your book, table 3.1. I put it in the end of your homework, and it lists all these different molecules you might run into, and it gives you the pKa's for them. On a test, I would give you, for example, the pKa's. I would either give you the Ka's for both of the molecules, the pKa's for both of the molecules, or what I'll probably do is I'll give you a Ka for one and a pKa for the other. And what you would do there is just take the negative log of the Ka, that turns it into a pKa, and the smaller pKa is the more acidic compound. But let's see how this plays out when they give you these pKa's. So here we've got this molecule. If you notice, that's right here on this table. And so the pKa for that is 9.9. The other molecule, water, you would see that here. The pKa for that is 15.7. So, the stronger acid, the more acidic compound, has the smaller pKa, and therefore the stronger acid here is this molecule, which is called phenol, because it has the smaller pKa. We go through the same procedure for the next one. We're looking for this molecule. We find it right here. The pKa is 18. For water, we just saw it, 15.7. Oops, it's 18. So, 15.7. The stronger acid has the smaller pKa, and so that is water in this case. That's the more acidic compound here. Third one, we have NH3. That has a pKa of 38. Oops. And then, so that's ammonia, pKa of 38. The name for that molecule is acetylene. You would see that just above it, it has a pKa of 25. And so here, which one is more acidic? The one with the lower pKa. That is the more acidic compound. We can go through that same procedure with these next ones. We're just looking for pKa's. Whichever one has the smaller pKa is the stronger acid. So H3O plus, we would see that right here. It has a pKa of negative 1.74. HCl has a pKa of negative 7. The stronger acid is HCl. It has the lower, the more negative pKa. In this next molecule, and the next exercise, we see here ethane, that's what that molecule is, and that is given way down here at the bottom. It has a huge pKa of 50, so that is barely acidic at all. Remember, because we took the log, each p unit is a power of 10, so pKa of 50, that's a lot of powers of 10. That's not very acidic. The other molecule, acetylene, has a pKa of 25. So the more acidic compound is the one with the smaller pKa, the more negative pKa. The pKa that would be more to the left on a number line. And so that here is that acetylene that I highlighted in green. All right, so then, for this last one here, we can compare these two molecules. We're looking for, first, that carbon double bonded to oxygen with the hydrogen on it. We see that that there has a pKa of negative 7.3, so it's pretty acidic. When we look for the other molecule, which you might recognize as sulfuric acid, right, H2SO4, when you look at that other molecule, you would see it's right above it. The pKa has a pKa of negative 9. Very, very negative. So the one that's more negative is sulfuric acid. And that is the more acidic compound there. So you can use these pKa's, and you could also use Ka's to compare quantitatively the strengths of any two acids. And in this case, I would give you the pKa's. You don't have to memorize the pKa's on this table. You would have to be able to think through them, though.